So now we're going to go over some of these reactions. And we start with this first one. We can see that the functional group we start with is an alcohol. And we have our chromium-based Jones reagent here. Now we know that this reagent gives us a couple possibilities. And it depends on whether we're starting with a primary or a secondary alcohol. Here, since we're starting with a secondary alcohols can only be oxidized to ketones. And that's regardless of the reagent that we're using. And so our second example, right below it, same situation. We have a secondary alcohol that gets oxidized to a ketone. Our third example in number 1, our alcohol is now primary. Primary alcohols, we have more options. In the presence of a milder oxidizing reagent, such as we talked about PCC, a primary alcohol gets oxidized to an aldehyde. But with this stronger oxidant, a primary alcohol will get oxidized to the carboxylic acid. Number 2, we have alcohols again, but in this case they're reacting with sulfuric acid, which is a protic acid, and heat. This combination of reagents will lead to a dehydration. Remember, that's where we're going to remove the OH group, as well as a hydrogen on a neighboring carbon to give us an alkene. Now, in the first example, it doesn't matter whether we remove the one that I did or a hydrogen on the other side, because the molecule, at least in terms of the alcohol, is symmetric. And so we would have gotten the same product regardless of which side we removed the hydrogen from. But in this second example, we have two possibilities. If we remove the hydrogen in green, we get that alcohol, or that alkene. But if we remove the one in red, we form that alkene. Is there a preference for one product over the other? The answer is yes. The preferred product is the one on the right. Why is that? Well, remember, according to Seychev's rule, that in an elimination reaction, the more substituted alkene is favored. The molecule on the right, the alkene, has 1, 2, 3 substituents. Whereas on the left, this alkene only has 2 substituents. So this is less substituted, and therefore it's going to be the minor product. And the one with the more substituted alkene will be the major product. Question 3 here, we're filling in the reagents. We can see that we have a primary alcohol, and that primary alcohol is being converted into a carboxylic acid. How do we do that? We do that using the dichromate or Jones reagent, and that's what allows us to do that in one step. Alright, question 4 says, assume that you have these two compounds that are drawn below. They both have the same chemical formula. But when we add them to sodium hydroxide, only one of them dissolves. So how do we use that to figure out which one's which? Well, we've talked about phenols. Phenols are compounds where the alcohol is directly attached to the aromatic ring. Phenols are much more acidic than alcohols. The compound on the left is not a phenol, it's just a typical alcohol. The reason it's not a phenol is that there's this extra carbon here in between the OH group and the aromatic ring. So if we consider the pHs or the pKa's of alcohols, many alcohols are not acidic enough to react with sodium hydroxide. But phenols, because they're directly attached to the aromatic ring, can be deprotonated by sodium hydroxide. So how does this help us to answer the question? Well, are alcohols water soluble? As we've learned, the answer depends. What does it depend on? It depends on how many carbons they have. Both of these molecules have 7 carbons. So in general, they're not going to be water soluble. But in the case of the phenol, the one on the right, if we add sodium hydroxide to it, sodium hydroxide is strong enough to deprotonate the alcohol, gives a sodium salt, and that molecule is completely water soluble. So even though these two compounds have the same chemical formula, the fact that one of them dissolves in sodium hydroxide tells us that it has to be that one. All right, question 5 says that the alkenes drawn below can be made from dehydrating an alcohol. So what's the alcohol that could be the starting material? Well, this first one's probably the easiest one because it's symmetric. And so if we're going to dehydrate, that means the 2 carbons of the alkene, one loses an OH group and one loses a hydrogen. And again, because this one's symmetric, we could have reversed those, but regardless, it would have gotten us to the product. The second one we could put the alcohol there. Or there. Again, does it matter where we put it? Because in some cases it will, but in this example, again, it won't. Because regardless of where I put it, this is the alkene that's going to form because it's more substituted. And in our third one, it also doesn't matter which carbon I put it at. So I could make that the starting material. Or that, because there's no other carbons where the elimination could take place. Alright, question 6. What would happen if we oxidize the following alcohols? In other words, if we oxidize them, what's the product? Now this first one is primary, so it really depends on what reagent we could use, because it could turn into the aldehyde, or with a stronger oxidizer, it could convert to the carboxylic acid. The second one, being secondary, has to form the ketone. Same type of situation in this third one. We have secondary alcohols, they get oxidized to ketones. And finally, this last one is a tertiary alcohol. Remember, oxidation requires us removing a hydrogen from the carbon that has the alcohol. Since that carbon has no hydrogens on it because it's tertiary, that cannot be oxidized and we'd get no reaction to take place. All right. Finally, number 7, we're dealing with this compound 2,5-hexane dithiol. And we're saying that oxidation of it forms a 6-membered ring. So remember what happens when we oxidize a thiol. We form a dithiol. Well, if our two thiols are within the same molecule, they could bond to each other. And so we could form, and let's do this in a different color, a new bond between these two sulfurs that would form a 6-membered ring. And so we're still forming a new bond between these two sulfurs, just like we did above. It's just going to make the molecule cyclic. Now that's probably not the way we want to draw it, so we can convert that to a better looking drawing. But the product is the same, that we get a 6-membered ring. Now, something like this for dithiols works very nicely when the result is a 6-membered ring. If you were dealing with a situation that would only give you, say, a 3-membered ring, then this reaction wouldn't work in this way. But when you can form a 6-membered ring, those are generally very stable and are happy to form.